Okay folks, I will make this video before my sweetheart goes home, because then I can't concentrate. So I wanted to talk about control signals and how to make these equations, logic equations. So to write into the registers, the CPU needs to set the chip select and the read and write line. And what's produced here is two strobes, which one of them is write and the other one is read. Those are mixed in with the address decoders, so when the CPU wants to write, then it sets also the address bus. I forgot to say that. So it sets address bus, chiplet select, read write, and then the clock signals come along and clock all of this together. So you will also need clock inputs, and those are up here. There are two of them. And also, just as a reminder from last time, when we are writing to these registers, this is the memory element and this is the data line. This is write. So let me just do this, and this is the read strobe. It's not the same as the two coming in here, because they are mixed in together with the decoded signal. What happens then is that this one will fire and you will get data from the register. This output here will drive the data line. So enough about that. So that is just a little bit repeat from last time. So let's go back. And this clock signals, I'm looking at those now. But you need this two clock signal, and I call this VIC II and the VIC III. So yeah, here you can see I'm working on the clock part, and you can see it's a lot of work. And you can see that the only clock that comes in for this part is VIC in. It's about 8 MHz, depending on if it's PAL or NTC. And then you have the call clock. And then this VIC chip, this also delivers a reduced clock frequency, about 1/8. That's 1 MHz of 8 MHz. So this goes to the CPU. So you can see that the V in comes here. It goes into this register here. It's not a register, it's logic element. It's inverted, and then these are basically an advanced inverter with it's like a latch. Why couldn't you just use the inverter, right? You have V in here and you have V in here. Why can't you just take the signal out here? Well, that's the thing. This is the part I'm talking about. The thing is, when you have registers, you want to prevent something called race conditions. A race conditions, that's something you get when you have like an output, inverted output here, connected back on the input of the register. So what you want to prevent is that the output changes the input and the output again. So if these inputs and outputs are on at the same time, then you will have like a possibility of an oscillation. So after making this, and you can see all these numbers I put here, those correspond to the numbers you can see here. And the reason why I did that was you don't stand a chance unless you have photographic memory or something. Because you get lost pretty quickly when you try to derive the circuits here into a logic diagram. So let's have a look at the chip select then. Okay, so let's figure out. These are outputs, and we have inputs here and here and here. So the first thing you do is start writing what's what. And up here, this is an inverter. It's easy to see because the output can only pull it down. And this part here pulls it up again, so this must be chip select, non-inverted. And then you have up here you have read write inverted. Okay, and then this one is also the same. You see they are connected together. You have the same thing over here, so just continue. Inverted. Therefore this line here must be the inverted, because there's an inverter again, like this, without the bar on top. So therefore you have read and write again. And you see this chip select goes over here, and the output is called chip select inverted. So therefore you have chip select inverted here also over here. And now it becomes a bit more tricky. But let's continue with the inputs. So this is let's see, what are those? They are VIC and VIC II. It's not a big deal, it's just for the video. So this is V. So let's write it in here. So okay, so what's going on here then? Yeah, so the first we need to find out what's connected on the outputs. Are they connected anywhere else? Because if they're connecting anywhere else, then we need to AND or them together. But this part here is not, so this is just connected to another gate. So this part here is actually, to pull this low, then you have to go through two gates. That means this is right, so that's VIC II and 3. This one, it goes through this one into that one. So then you have VIC III over here. So we have ground here and here, but we have an output here. And this output can be driven this way, or it can be driven this way, or this way. So therefore you have 3 ORs. So let's have a look at that. So you have chip select. Okay, and the last one is VIC II and 3. Yeah, I see. I was expecting to have a bar over here, and there should be also. But why was it missing? Yeah, that was because VIC II and 3, when those are on together, then this will pull low. So this has to be negate the logic like this. I forgot that. Sorry about that. But okay, now you can see why it has to be like that. So now you have the equation for this one, and this one goes over here. And what happens to it here can be pulled either to ground this way or this way. And then when it's not pulled, it's pulled up to 5 volt this way. So, but I have ignored that for now. So But you can see it's the same net. These two gates are on at the same time, so it's only one way. And this is basically just an inverter. So you have an inverter. So if you now we cheat a little bit, we say that this is not this lane anymore. This is this part over here. Then you have to invert the whole shebang. This. So yeah, that doesn't look very pretty, does it? So but you will see shortly that this becomes very clear what actually is going on here. So what I'm going to do now is I'm gonna simplify it. We have something called De Morgan. So this is his theorem. So you can do divide everywhere there's an operator and a bar, and when you do that, then you're splitting this beam over each term. And when you do that, you also have to change the operator. So that's De Morgan. You know, you have in Boolean algebra, you have all these rules. So this is Boolean algebra. I'm dealing with, sorry if I haven't told you. Let's say you have A and A not. This is one rule. Well, this will always be 0. So that's one rule, because if A is 1, then A not is 0. So 1 and 0 is 0, always 0. So if you have A is 0, then A not is 1, then you have 0 and 1 equals 0. All of these rules are really boring, but they are important. So, and this rule is also one of them. If you OR 1 with something, it will always be 1. And then lastly, you have this De Morgan theorem, and that's if you have like you have several signals, you can have C, D, E, etc. If this one is negative logic, you can change the operator, but you have to split the beam though. So like this. That's De Morgan. You can also go the other way. You can say A and B beam equals, and if you split it now, you get A or B, and you have split the beam. You have to change the operator like this. So yeah, so that's what I'm doing right now. Yeah, so this is the continuation. You split the beam, and then you can see here that double negated equals no negated, so we can actually remove all those doubles. And another thing I forgot to do was to change the operator. So yeah, I just copy this one like this. Now it becomes more clear what's going on here. So when all of these are on at the same time, only then you will have a strobe going high. What's this part here? Well, since this one is high now, we can just call it for R, because when it's low, then this term is 0, so then it's not active. So I have decided to call this read because of that R over there. So I call all of this for read because this is algebra and we substitute long equations with a simple term or long terms or without a simple term, because we are lazy and I'm lazy. So yeah, so we have read, and therefore this part here is then read not. Yeah. And here you can see I've already written it, so. And the same thing goes for the other one, so I can show you that, but it's basically the same thing also. And now the question is, why do they send the negative one away? Well, sort of, we did get an idea about why here, because OR statements aren't that useful when you're trying to make like a strobe, because then you want to add them together such that it's only strobing when it's active high, because when it's active high, then you know a high gate will then pass through whatever it needs to pass through, and not when it's low. So to explain that, we have to go up to the registers. Okay, so I have another document here, because these documents, it gets large, so when I work on them they tend to clog up, so I have several of them. In here on the registers and the register coders, you have negative write and negative read, and we'll see shortly why you need those in negative form. And this is so-called sprite enabled register, and that's $15. So when you have $15 on the address bus, you have this one goes high, and you need it to be negative. So there you have an inverter here, therefore you get $15 negative or inverted, and that's on this line. And this line here is, it's read inverted. So yeah, you can see it over here, it's read inverted, and it is then ORed together with this one. And here I haven't shown you the calculation, so let's look at write instead. Write inverted comes in here. You can drive this one up to ground, or you can use this $15 inverted to drive it to ground. Therefore you get this equation, and it's this part or this part can drive it to ground, which is this bar signifies that. And if you apply De Morgan, you will split this beam in two, and you get bar over bar is no bar, and bar over bar is no bar, and you change the operator. So therefore you get, that's why you need this bar here, such that you get bar over bar, right? Such that you get no bar. So if this one is decoded and the read strobe is strobing, such to say, then this line here is then active. So we can follow it if you want. This is, so this will be the 15th, and I think it will go through all the registers. Yeah, you can see it over here. This is something I didn't look at before when I looked at these registers, because I hadn't checked this, but this is actually a sprite enable. So here you can read out the sprite enable out on the data bus. So when this is going high, then the output enable is then driving the data bus.